There is no potential difference between the ends of this coil of wire. How then does the bulb glow? A magnetic field gives rise to an electric current in a conductor due to electromagnetic induction. In this lesson, you will learn how electric current is induced due to a magnetic field. You just observed that there was no electric cell to maintain a potential difference across the circuit. Yet, the bulb started glowing. When the wire is moved across a magnetic field, the free electrons in the wire experience a force that makes them move through the wire, inducing an electromotive force EMF, and thus an electric current in the wire. This process of generating an EMF in a conductor by moving the conductor through an external magnetic field is known as electromagnetic induction. When a conductor is moved in a magnetic field or kept in a fluctuating magnetic field, the magnetic flux linked with the conductor changes. This change in magnetic flux induces an EMF across the conductor. The EMF generated in this way is called an induced EMF, and the resulting current is called an induced current. The phenomenon of electromagnetic induction was first studied by Michael Faraday. Michael Faraday hypothesized that current induced in a coil is due to a changing magnetic field. To test this hypothesis, he conducted an experiment. You can observe this experiment to verify Faraday's law. To conduct Faraday's experiment, we will begin by winding an insulated wire over a hollow paper cylinder to make a coil. Next, we connect a galvanometer to the coil. Finally, we insert a powerful bar magnet in the cylinder with the south pole entering the coil first. We observe that when the magnet is moved in, the galvanometer needle deflects towards the left. When the magnet is moved out of the coil, the galvanometer needle deflects towards the right. If the magnet is not moved inside or outside the coil, meaning the magnet is stationary, the needle immediately returns to zero. The deflection of the needle when the magnet is moved in or out indicates that a current has been induced in the coil. Thus, an EMF is induced in the coil due to the movement of the magnet. Faraday's experiment confirmed that a moving magnetic field is necessary for electromagnetic induction. The direction of deflection of the galvanometer needle depends on which pole is inserted in the coil first. For example, in the experiment you saw, if the magnet is inserted with north pole first, the needle will deflect in the opposite direction as that of the previous case. In Faraday's experiment, you observed that a relative change in a magnetic field induces EMF in a conductor. The magnetic field can be changed in two ways: by relative motion between the coil and the magnet, as you saw in Faraday's experiment, or by winding two coils on the cylinder near each other, as shown. In the second case, one coil is connected to a battery with a key. This coil is called the primary coil. The other coil is connected to a galvanometer and is known as the secondary coil. When the key is pressed, a current passes through the primary coil. This current produces a magnetic field. As the magnetic field around the primary coil increases, the magnetic field associated with the secondary coil increases equally. The change in the magnetic field associated with the secondary coil induces EMF in the secondary coil. This EMF can be observed through the deflection of the needle in the galvanometer. The quantum and direction of EMF induced due to electromagnetic induction depends on 5 factors. Let's examine these factors one by one. The first factor is the direction of motion of the magnet in a coil. This determines the direction of the induced current. If you insert the magnet in the coil, the galvanometer needle deflects in a particular direction. When you move the magnet out, the needle deflects in the reverse direction. Thus, the direction of current gets reversed when the direction of motion of the magnet changes. The direction of the induced current in the coil also depends on the orientation of the magnet. If you move the magnet into the coil with its north pole first, rather than the south pole first, the direction of the induced current in the coil is reversed. The speed of motion of the magnet through a coil determines the strength of the induced current. Thus, if you increase the speed of the motion of the magnet, the EMF generated increases, and vice versa. The strength of the magnet is another important factor. The quantum of EMF induced in a coil is proportional to the strength of the magnet. The stronger the magnet, the higher the induced EMF, and thus increased induced current in the coil. Finally, the number of turns in the coil also affects the induced EMF. Using a coil with a greater number of turns increases the induced EMF. Based on his experiments, Faraday postulated a law on electromagnetic induction. Faraday's law states that the induced electromotive force E in any closed circuit is directly proportional to the rate of change of the magnetic flux through the circuit. You can determine the direction of the current induced when a conductor moves in a magnetic field using Fleming's right-hand rule. This rule is also known as the generator rule. To use Fleming's right-hand rule, stretch the thumb, the index finger and the middle finger of your right hand so that they are at right angles to each other as shown. If the index finger points in the direction of the magnetic field and the thumb indicates the direction of the motion of the conductor, then the middle finger indicates the direction of the induced current in the conductor. Consider a conductor AB connected to a galvanometer placed in a magnetic field. The direction of the magnetic field is from the North Pole to the South Pole. When you move the conductor up, the galvanometer needle deflects to the right. This rightward deflection indicates the direction of the current in the conductor from end A to end B. If you move the conductor downwards in the magnetic field, the galvanometer needle deflects to the left. This indicates the direction of the current in the conductor from B to A. Thus, you can see that the direction of the magnetic field, the movement of the conductor and the induced current are at right angles to each other.